Today's lecture is going to outline Chapter 5 in our textbook of Tarbuck, Luckens, and Tassa for honors or science here at Deerfield High School. So it all starts off with the hydrologic cycle, or the water cycle. The water cycle is driven by sunlight energy, we call radiation. Heat energy changes atmospheric conditions and temperatures, thus changing the state in which water can be found on our surface. In this case, we're talking solid form of ice, liquid and water form, both salt water and fresh water, and as a vapor in our atmosphere that we just consider in the gaseous phase. So in this case here, this is kind of a general depiction as to how water can go from one phase to the other, and once again we're talking about radiation being the driver. That there is no starting or stopping point of the cycle. It is continuous. So Earth is a system, the hydrologic cycle itself. Water is just about everywhere on Earth. It can be found as a solid liquid in its gaseous state. Water dominates the Earth's surface in the oceans as saline water, making up about 97.2% of all water found on Earth. The remaining 2.8% of all water found on Earth is fresh water, and most of that is actually frozen as ice in glaciers. So if I look at this pie chart here, this kind of graph that I'm looking at, this visual, most of the fresh water is found in this glaciers itself. So the hydrologic cycle, no beginning, no end. Well, see, all rivers lead to the sea, yet the sea is not full. So what's happening here? Well, the sunlight energy that's driving the water cycles is constantly in different states. That sometimes we're looking at it from the evaporation phase. Sometimes it's in a precipitation phase. Sometimes it's going to be as seen on the earth or observable as runoff. But all the while, this rain is actually doing work. It's constantly changing its form, it's constantly changing its phase, and it's eroding over time. So these mountains here, over the course of, say, tens of millions to hundreds of millions of years, can be broken down physically, weathered by the rainwater. So it's able to do work, and that's why water is a sculptor and a shaper of Earth's surface. So what's a drainage basin? Well, the Mississippi River drainage basin covers the central parts of the United States, right, the heartland of the United States. And its boundaries include the Rocky Mountains to the Appalachian Mountains. And all of these rivers within here kind of flow into one general direction, and they reach the Mississippi River. And that's what we call watersheds. Watersheds themselves. We are located up here in the upper Mississippi River basin. And these rivers take on what's called a dendritic form, where we see smaller rivers building and feeding into larger rivers. And as it continues to have more and more tributaries that build into it, the total stream flow, the total amount of volume of water continues to increase. So the Mississippi River is the largest in North America, thus has the largest number of tributaries that feed into it. So these tributaries are the smaller rivers here. So there's four primary drainage patterns. We have this dendritic phase, and this is what we're looking at. This phase is where we have these little tributaries that are continuing to feed it, and it continues to get larger as we see it, as more and more feed into it. Here's a radial pattern. If we look at it from, say, a mountain view or a volcano, it's moving from one central location away in all locations. We can have a rectangular, and we can have a trellis form, and you'll read a little bit about those in the textbook. So if we look at Illinois watersheds, right, including the Chicago and Illinois rivers, we're looking here, we're kind of located in this area right here. And all of these different colors are the different watersheds. And these watersheds are really just based on the geology and the elevation of the land in and around Chicago. So here we can see that the drainage basins here are separated by what we call divides. And the divides then redirect the river systems in different locations. So the land area that contributes to the river system is called a drainage basin. The drainage basin of one stream is separated from the drainage basin of another by an imaginary line called a divide. Divides range in scale from a ridge separating two gullies on a hillside to a continental divide, which splits whole continents into enormous drainage basins. DHS is located near a continental divide. So the continental divides of North America here, and I'm just going to focus on the United States for a minute. If water lands on DHS, it can flow through the Middle Fork River and eventually makes its way to the Gulf of Mexico. But if it flows just a little further east, or lands on and becomes runoff and flows into the Great Lakes, it's going to travel through the Great Lakes region and out through the St. Lawrence Seaway, and it's going to eventually reach the Atlantic Ocean. So A drop of water that lands in a very, very short distance proximity from one another can end up in totally different locations, as we can see here. So looking at the watersheds of Illinois, that's really the result of glacial landforms, and these are called moraines. So here's what we have. This is a watershed map. Just kind of different colors are the different watersheds of different regions. Well, this picture here is a geologic map or a landform map, and these dark lines are moraines. These are landforms, glacial landforms that were left behind during the most recent Great Ice Age. Right, the local landscape here in Illinois was shaped from glaciers during the Great Ice Age, and this ended about 10,000 years ago. But if I superimpose the landforms onto our watershed map, you'll see that, well, the landforms are what are, these moraines are the sculptors and the shapers. These are directing the flow of water. So the glacial landforms called moraines in black above that are superimposed on these different maps here kind of help determine or help tell the story of how and where water flows in Illinois. All right, moving on to stream order. Stream order is a term used to identify the size and structure of a waterway. The smallest streams refer to tributaries, or the lowest or smallest number. Tributaries feed into larger streams. Larger streams have larger numbers. So stream order, we've got these smallest rivers flow into larger numbers. These larger numbers continue to get larger downstream. So this water here at location 4 right here contains water chemistry and parts from all of these different bodies of water that we see. That this water here is kind of composite of all of this water upstream. So meandering streams. So sometimes the downstream migration of a meander is slowed when it reaches a more resistant material. This allows the next meander to catch up and overtake it, creating a shorter channel called a cutoff, and eventually an oxbow lake. So clay, a very fine sediment, plugs up the channel, diverting it to its new path. So a meander, we're really talking about the bend of this river here. It can actually get, let's just say, plugged up, and it changes the path of this river. So an oxbow lake is the feature that results. So as the river ages, it evolves. Generally speaking, an older river has more or greater sinuosity, a greater amount of meander to it, and eventually it can become an oxbow lake. And this is a result of erosion and deposition within the channel. So this sequence here, I would say we could see that the amount of meander is going to increase, and you're going to create these landform features as a result. So braided streams. So some streams consist of a complex network of converging and diverging channels that thread their way among numerous islands or gravel bars, and that's what we're seeing here. It looks like braids of hair. Because the channels have an interwoven appearance, these streams are said to be braided. While meandering streams carry suspended loads in solution, braided streams generally carry loads of fine and coarse-grained particles. And this is what the water is transporting. It leaves it behind, thus changing this network of the paths in which it flows. So a stream channel can be thought of as an open conduit that consists of stream bed and banks that confine the flow of water, well, except during floods. So when we look here, two main types of channels are called meandering channels and braided channels. The meandering is what we looked at prior. The braided is another example of what we're looking at here. Floodplains. A floodplain is a flat area immediately adjacent to a stream. It may be covered with water during periods of high discharge or flood stage. Lateral movement of an active channel is caused by erosion and deposition, creates additional features in the floodplain such as meanders, oxbow lakes, natural levees, and splays. So here's a general picture here. And over time, we'll see that this really flat, straight river, in this case here, the stream here that's cut through, is eventually going to gain or add meander as its floodplain evolves. And then over time, the rivers change their paths. And this is what we're looking at here, time vector. Sediment being transported is deposited, and in some places land is eroded. Here we can see that streams evolve over time. That the outside of the bend, or this cut bank, is being eroded, where the inside is actually a point of deposition. And this is what's called a point bar. And we can get sand and just different types of gravels that build up on the inside, whereas the outside is eroded. So it's going to be changing the amount of meander, or the sinuosity of the river itself. And here's kind of a picture before and after. And we see that this erosion takes place. There's this tremendous amount of land, and then all of a sudden, well, it's right next to the shed. Erosion took place on the outside, deposition takes place on the inside. So runoff and erosion. Well, water that falls as precipitation on land can lead to erosion. Erosion is a physical and or chemical breakdown of something. Land, even mountains, can get eroded over time. Water is a sculptor and a shaper of the land, constantly eroding rock and soil and transporting it downstream. In the picture we see that there's a balance to this water cycle. It is said to be in equilibrium. What gets evaporated later comes back as precipitation, and that can be in snow, ice, or liquid form. Moving on. So here we can look at the characteristics that we've looked at with rivers. So rivers have different characteristics. There's a different way I can compare a pool and a riffle system when I'm looking at the speed of what's taking place. I want to pay attention here. You need to make sure you differentiate these pictures. So as characteristics change, so does the velocity of water. So here we can see three different types of characteristic river patterns. The pool compared to the riffle. Well, the riffle is going to be shallower, and because stream flow at the riffle must be equal to that of the pool, the shallowness leads to an increase in velocity. So stream flow, we're talking about width, depth, velocity. If it's shallower, it must travel faster to compensate for total stream flow. At this picture right here, we have a bend in this river. You'll notice that location C is going to be the cut bank. This is where you're finding an erosional environment, or erosion taking place. And D is the inside. The velocity of the water decreases as it makes this turn, and therefore this is the region of deposition. So on the inside of the bend I have deposition, on the outside I have erosion. And this is going to then thus increase the meander or the sinuosity of this particular part of the channel. And then to the left, where we find the deepest water, on the surface we're going to find water traveling the fastest, simply because it's furthest away from frictional drag. So this is an asymmetrical channel, and you'll find that location D would, in theory, have the greatest velocity of water. So the velocity of water is important. It's going to be involved in the transportation, the movement of sediment and water. So the brown water in the picture is the suspended load of sediment, giving the water a muddy appearance. So as water flows, it carries sediment with it. The competence of a stream is the maximum size of particles it is able to carry. A faster moving stream has greater kinetic energy, thus is capable of having a greater competence. It can carry larger particles. Doubling a river's velocity quadruples its competence. But the capacity is the maximum load that a stream can carry. The greater the volume of water, the greater its capacity. Thus, a river in flood stage has a much greater capacity and generally will have a greater amount of competence as well. So let's look at the sediment that's being carried. We have three different terms that we'll reference here. Dissolve load. This is what we measure using sophisticated instrumentation. This is why we use the spectrophotometer. But the suspended load is really what we see as murky. This is a measure of turbidity. So dissolved load is a part of the solution of the water itself, whereas suspended is literally being held in by the kinetic energy of the water. And the bed load is what we see taking place as kind of rocks, pebbles, gravel are kind of moving in small bursts forward. And eventually they get rounded off. Rocks get rounded by abrasion within the bed load. It's a physical or mechanical weathering as they roll and bounce along the riverbed. Angular edges get smoothed off over time. They're actually referred to as river rock. So the concept of erosion is really just breaking something down. So erosion can actually lead to what are called potholes. Not the potholes you think of in a road, but they're kind of similar, but they're a little different. That if you get a particle, a grain of sand or a rock that's caught here, and you get kinetic energy of water, it swirls it around, and over time the rotational motion of the swirling pebbles acts like a drill, creating these potholes. But erosion takes time. It does not happen instantaneously. When we look at a depositional environment, right, water breaks things down, it also builds them. We can look at deltas. Deltas are depositional environments. It's where sediment ends up. And in this case here, a simple delta is where the speed of the water slows down enough so that the water doesn't have the kinetic energy to transport the sediment, and it literally builds a structure. And we can see this most prominently when we look at the Mississippi River Delta, that here are different deltas that have evolved over time. That Louisiana hasn't always looked at this. During the past 5,000–6,000 years, the Mississippi River has built a series of 7 coalescing subdeltas. And these are just different forms of the path of which the river deposited sediment that was transported along the way of the Mississippi.